Welcome to this first video for this lecture in game theory. I'm Leonardo Badia. In this part, we'll discuss the problem of commons, which is a general perspective on all these competition problems in the society, and it is often considered from the perspective of good citizenship, but is also a problem in many allocation problems in engineering. Let's see what is the tragedy of commons. Many philosophers, even in the past, the first one to formalize this was Hume, but even prior to that, there were other philosophers and thinkers pointing to it, that people tend to misuse public resources. And you see, environmental pollution, but even on a smaller scale, like garbage thrown on the street is an example of that. And there are several ways of formalizing this. The classic version was formalized by Harding in 1968. And the idea is that we have a population of N farmers in a village. They have goats. They breed these goats, and the goats can eat the forage, can pasture on a common green area. So each farmer owns GI goats. The total number of goats is big G. And each goat costs C in expenses for the stable and for cleaning the goat and caring after her. So you have a fixed cost of C per goat. Now, the thing is, the benefit instead is the use of the common green. The common green has a different value per goat that depends on how many goats use it. And the bigger the total number of goats that pasture on the common green, the lower the individual value per goat, because there will be less grass to eat, let's say, in short. So we have an individual value, which is a benefit of the foraging the goats on the common green, that is VG decreasing with G. So we can represent this with this function. But let me remark, okay, why is this talking about goats and farming and common green? Well, there are a lot of situations, especially my mind comes to the Wi-Fi hotspots, where the situation is exactly identical. If I say, well, there is a common Wi-Fi at the university, of course, the quality of the Wi-Fi depends on how many computers are attached to it. So ideally, you would like to be the sole user of the Wi-Fi, so you have a very high bandwidth connection. And it's not even a perfect share, because if you know a bit of interference, well, the interference is even more damaging to you than, if there are two users already, sometimes you even get less than half the bandwidth. So in general, there is a generic rule, VG, according to which the value decreases. So we can think of something like that. VG is decreasing in G, and also has, is a concave function. So second order derivative is also negative and reaches a top value after which the value is 0. So there are really too many connections or too many goats. Okay, this is just an assumption that we can make. Now, where the tragedy comes from, the payoff that you get from, what is your choice? The choice is how many goats to own for the farmer. And if you are instead a Wi-Fi user, how much bandwidth to request to the Wi-Fi hotspot. Okay, whatever. The payoff is the number of goats you have times the benefit minus the cost. The benefit is the individual value of VG. The cost is fixed and equal to C. So for brevity, let's write G minus I, as usual, as the number of goats owned by the other farmers. I am farmer I, and the other farmers own G minus I goats. And let's find the Nash equilibrium. The Nash equilibrium is, I want to find the maximum GI, given that the other players are playing a best response. So it's the same function as before. Once again, this is continuous, but it's easy to solve, so we allow for it for probably the last time. Now, how to find this GI? Well, we remark that GI is involved in this maximization 2 times, similar to the Cournot duopoly. So it's a bit trickier that you cannot simply say, well, you compare with the cost. No, it's also depending on the value. So if you increase GI, you see that you increase your revenue, because you have increase your number of goats, so increase the total gain, but the unit gain can decrease. So you don't push your number of goats too high, because if you own too many goats, this will increase, but this will decrease. And so if the value is 0, you are left with a negative reward. So you don't want to do that. Let's maximize this. And to do so, you need to get this with a trick, because this is a bit difficult to solve, because we don't have, differently from the Cournot duopoly, the exact expression for VG. So what we do is like this. We exploit symmetry, because remember, in Cournot, we found out that there was a symmetry. Two players, they share the resources. And so it's logical to expect that if there are n farmers, they will get an optimal quantity of goats that is equal for everyone. So Gi star will be total G star divided by n. So let's put this inside. And this gives us a hint on how to solve it. Exploiting symmetry will allow us to solve this equation. Now, if we solve this, we want to maximize this function. And note that this V, I don't know what the derivative is, but when I take the derivative here, I have, first of all, I derive this G, and so I get this expression. And second of all, I instead keep G constant, so it's G star, but I derive this expression. So I derive this expression and I get V prime G star divided by n. Okay, so G star divided by n times V prime G star. This is the derivative, and this must be equal to 0, correct? So we expect this to be solved in some way. We don't know, because we don't know the expression for V and V prime, but we can derive this condition. Now, the thing is, we have this condition at the Nash equilibrium, and the point is, what happens instead if we consider the global welfare? So we consider, similar to the Cournot duopoly, like all the farmers agreeing on acting like a monopolist. Well, not really a monopolist, but a single player. So they decide what is the best number of goats we should have. The best number of goats has an optimum for which this holds, correct? Let's check this. The total utility is the sum of all these quantities. So you can find that this is the optimum quantity of goats, total number of goats. And this is also equal to 0, because the optimality is found by maximizing the total welfare, so this derivative must be equal to 0. And since they're both equal to 0, let's equate them. What do we find? We find this situation, that Gm is generally a lower value than G star. What's the reason? The reason is that, well, at the Nash equilibrium, this holds true. And the reason why we have this equation is that assume you are a farmer with G goats. You might consider to increase with an increment H. What happens is, well, the cost of your possession is increased by a factor C. Also, you gain value because you have more possessions, but the value of the possessions lose a bit of value. How much? Well, this VG plus H minus VG divided by H. Well, this for H tending to 0, this is nothing but incremental ratio. So this is the reason why you have V prime of G. This is the first order derivative. And at the symmetry, all the users have Gi equal to G star divided by n. This is something I remarked already. Now, the key point is that you can do the same reasoning for the total welfare. So I say my welfare, if I consider buying one more goat or an incremental fraction of goats, goes like this. This must be equal to 0, meaning this is the increased benefit I have from more goats, must be equal to the decreased in benefit I have from more goats. I have higher costs, and also I have loss of value. The loss of value I experience is divided by n. This is very important. It's divided by n because I incur a loss, but everybody incurs a loss in my action to buy more goats. Everybody is sharing my loss of value, and everybody gets 1/n of it. If I consider the social welfare, the welfare of the entire society, if any individual considers increasing buying more goats, there is an increase in value identical to before, an increase in cost identical to before, but there is a loss of value that is not divided by n, because now I'm counting the loss of value for the entire society. So the fact that I'm missing this 1/n term implies that I stop later, because if I'm increasing, accumulating goals and goals, I stop when the benefits are compensated by the loss of value. The loss of value is lower, so I keep increasing more. And this is why you have the situation that I showed you before. That is, you stop later. And this is exactly the same that you experience in public usage of resources. Like if you have a public library or a public transportation, you see, young, uneducated people, I hope it's not you, I don't know, stamping their feet or vandalizing the public transportation. Why they do so? Because it's fun. And they don't care because they don't act like it's theirs. So maybe some old teacher of yours told you, remember, public properties are also yours. So if you ruin them, you ruin it also for yourself. So in reality, there is no denial. You don't, put your feet on an armchair at home because you will ruin it. But maybe you do so on the train because, well, you don't care it as much as your own property. You care exactly 1/10 of the public property of what you care for your own property. So this is why public resources are misused, because the damage you cause in exploiting them is only 1/10 for you, and n-1/n for the entire society, for the rest of the society, not you. So you don't care. It's again a consequence of your selfishness, of the fact that you want to maximize your own utility, and you don't care if the other players have a low utility. Okay, so this is a very important concept. You can see this in a lot of resource allocation programs. And thereby, I urge you to consider any possible application. Of course, there is no solution. It's just a tragedy. And you must establish it can be modeled, and then you should figure out some way of solving it external. And that's where the engineer also comes to rescue. Okay, so once again, let's see a final topic, which is more engineering. I'm mentioning this because it's also a nice application that is now very classic. When I started presenting this, was very new result because it was derived at the beginning of the 2000s. So it's like a 15-year-old result. And nowadays it has become a bit of a classic. So these slides are already, they deserve a place together with the other models. But this is actually a very computer science model and not an economic one. Even though it has consequences on, industrial engineering or, road traffic as well. Let's see. It's called selfish routing. And the idea is what happens if you choose paths. There was a result in 1920, made by Pigou, of this simple scenario. You have two roads bringing you from a source to destination. And the two roads, in reality, if this is a graph, generally graph theorists don't like graphs with multiple arcs. So you can imagine this is not a simple arc, but there are multiple arcs, so there are two different paths. Anyway, it doesn't matter. But the cost on the orange route depends on the congestion, and the dependence is X. X is the fraction of traffic that takes that route. The blue route, instead, has a fixed weight equal to 1. So let's say 1 unit of traffic goes from S to D. 1 unit means the entire traffic, the 100% of the traffic that goes, for example, to one city to another when commuting in the morning at the rush hour. So they decide what road to take. Well, the point is, the orange road is a dominant strategy. So it is, in a sense, the Nash equilibrium. Why? Because if you go with the blue route, you are sure you take a cost equal to 1. If you go with the orange route, you get a cost that is lower than or equal to 1. So it's a dominant strategy, not necessarily strictly dominant, because it can be 1. And actually, it will be 1, because from the perspective of every individual, every single car, let's say, moving in the morning, the orange road is exactly identical. Well, why don't you move to the blue one? There is no incentive. There is no unilateral incentive in doing so. So 100% of the traffic will end up on the orange road, and 0% of the traffic will be on the blue road. So this can be like saying the orange road is like a high-speed route, a highway, and the blue road is a countryside road. The countryside road has speed limits. It passes through villages, so the cost is very fixed. You cannot go very fast. The orange road, if it's free, is very, very fast. Cost is almost 0, so the cost in this case will be the time to reach the destination, the cost is almost zero. But if everybody is taking the highway, there is a traffic jam. So it takes really as much as the other road to go to the destination. Well, nevertheless, there is no unilateral incentive in deviating, even if 100% of the people take the orange road. And this strange situation was noted by Pigou already. So let's see if this is really a problem. Is Pareto efficient or not? Well, it is Pareto inefficient because you can do better. You can do a better division of traffic. You can split traffic 50-50 like this. There is a nice animation. If you split the traffic in half and only half of the traffic goes to the orange road and half of the traffic goes to the blue road, this is an advantage because, well, actually it's not an advantage for the cars going on the blue road. They are identical to before, but the cars going the orange road only experience a cost equal to 1/2, and they are themselves 1/2. So 1/2 of the cars get cost 1/2. 1/2 of the cars get cost 1, so the average cost is 3/4. You can prove this is the optimal allocation. You can prove, if you don't believe me, you just take derivatives as we did before. Like you say, let's say X is the split, so X goes on top, 1 minus X goes below, and you find out the optimal X is equal to 1/2. So that would be the best possible solution, which also means that this is a Pareto efficient situation because you can't do better. Basically, there is no way of improving this because if you move cars from this allocation, they always get worse. So this is a way where cars cannot get any better. Still, it is not a Nash equilibrium because there is an incentive for cars in the blue road to move to the orange road. Unfortunately, this makes some cars in the orange road worse, but they don't care. In the Nash equilibrium setup, they don't care about the global welfare. They only care about their own welfare. So every car that is in the blue road has a unilateral incentive to deviate and go and take the orange road instead. This is done by every car in the end, so they will reach a Nash equilibrium where they all go through the orange road. And at this point, the situation is very inefficient, yet no car has unilateral incentive to deviate because they will get the same cost anyways. So you see, the total cost here was 3/4. In the Nash equilibrium, the cost is 1. So you can say the price of anarchy is 4/3. So you pay 33% more by letting each driver choosing their own preferred route. So it would be ideal that cars are sent according, I don't know, to some programmed GPS. Half of the cars are sent to the country road. This won't be beneficial for them, but will be beneficial for the cars in the orange road and will be the best social benefit. Okay, so this becomes even worse if the cost of the orange road is non-linear. So instead of the previous situation where the cost is equal to X, which is proportional to the congestion, let's consider a situation where the cost is X to the power of A, with very big A. Remember, X is lower than 1. So this means that as long as the congestion is lower than 1, strictly lower than 1, the cost is very low in general, because it's a number lower than 1 elevated to a very high power. But when X approaches 1, is 0.99999, it suddenly spikes and reaches almost 1. So this would say, okay, the orange road is a very good alternative, and you get to destination in almost no time, unless you all take it. When you all take it, it's very bad, because it will be congested. And well, you know what? This is exactly what happens in the Nash equilibrium, because then people will split like this. Even if you have a tiny fraction epsilon going below and 1 minus epsilon, this would be perfect. The fraction 1 minus epsilon going on top will have a cost that tends to 0. And the fraction epsilon below will also go to 0. Nevertheless, the top path is dominant. So in the Nash equilibrium situation, everybody takes the orange road. So the total cost is 1. You see, this situation has an infinite price of anarchy. So really, this depends. In the general case where you have a non-linear cost, you can have an unbounded price of anarchy. So if you were thinking, well, in the linear cost, the price of anarchy is 33% more. So it's 1.33. So meaning you pay 33% more than the best optimal case. Okay, I can accept that. But you see, if you have a non-linear cost, then the price of anarchy is unbounded. You pay infinitely more for being anarchical, which is not a pleasant result. Okay, and a similar paradox that I mentioned only for the sake of completeness is another situation identified by Bress. And this shows that sometimes you can have a Nash equilibrium that becomes worse, meaning less efficient, if you try improving the network, which is kind of strange. Let's see this example. Here, this network. This network has two identical paths. Well, not two identical, but similar paths on top and below. Because the optimal way of doing here is to split half and half, right? And the cost will be 3 halves. You can check. Because the upper route and the lower route are actually identical. You get a total cost that is 1 plus x. And if you split the traffic half and half, this will be ideal. But yet, let's say you arrange a connection between these two green nodes. A connection that is even cost-free. That's a crazy stuff, because you are adding a link without any cost. So you would think the transportation on this network can only improve, right? Well, not even in the close, because now everyone wants to take the orange road as before, and the cost will be worse than before. Cost will be higher than before, will be 2, despite you added a better route here. So this often happens, and is also mentioned, this paradox is mentioned by urbanists and urban planners, because sometimes, I don't know, a new highway is added to a city, and they find out the traffic becomes worse. There are more traffic jams than before. What's the problem? That they added a new very high-speed highway, and everybody takes it, so the traffic gets worse. So this is just to mention that graph theory and application to game theory are not as simple as you think. Okay, and finally, I'm mentioning this result because there is a theorem, which I won't prove here. That is the result that was found at the beginning, I think in 2003. There was found a detailed analysis, which is too complicated to report here, to show that in reality, you can prove that if you have a network, not just the 2-node networks that we showed before for the Pigou situation, but any network where latencies are linear, you can find that the cost of a flow decided as a Nash equilibrium is always 4/3 than the optimal flow cost. So this is to say the price of anarchy is 1.33. This is always the case for any linear latency, meaning that the case where you have Pigou situation is a worst case, because in this case, you have exactly this price of anarchy. So already to understand what's the problem with a network like that, you are happy enough with Pigou case. Any more complicated case always falls down to Pigou case. And actually, the intuition is that whenever you are confronted with 2 choices, well, selfish user take the better one, which is good for them, but leads to overload. So this does not depend on topology. It's a very nice result, by the way, because they found that the price of anarchy is a characteristic of the selfishness in this situation. And it can boil down to the 2-way alternative between the road with congestion cost and the road that has fixed cost with no dependence on congestion. So the price of anarchy in this situation is intrinsic. Okay, so well, this result of especially the constant of 4/3 as the price of anarchy is something that shows up in many similar situations. Like if you have, instead of linear latencies, you have latencies determined by queues with MM1 structure, or there are other situations with linear costs. Apparently, there are some motivation that still have to be found, for which there are this constant always showing up. And there are other scenarios in which the price of anarchy might be different. So in general, this can be a good idea for your project. Well, one possible idea for your project, if you're interested in it, it can be to study some routing-like problem and to identify some selfish solution to it and quantify the price of anarchy in this scenario. And more in general, I hope this lecture gave you the idea for your project. You see there are many open problems, and there are a lot of problems where engineers can really contribute. And so I hope there is a spark in your mind to have a good idea for your project and bring research further with game theoretic instruments. And this concludes the lecture of today.